Okay, now that we've talked a little bit about how they get together and we've looked at an atom that has a certain amount of available electrons, looking at those Lewis dot diagrams, and kind of seeing how those single dots, those single electrons, can get paired or shared with another electron, another single dot, and get together. We're now going to get a little bit more into the geometry, so the shapes. And again, don't be alarmed and nervous about the geometry. It's going to be really pretty basic. And again, if you know a little bit about angles, you'll see some of the geometry we're looking at. So the first shape that we're going to talk about is the linear arrangement. And a linear arrangement is just that. It's straight. So let's say we have something like two hydrogens together. All right, H2. Hydrogen gas is H2. Well, here's a hydrogen. There's one. There's another. So we have two of them, each with one available electron, and we can get that sharing between the two of them. All right. When I clean that up, obviously H dash H, that H, that dash is the shared pair of electrons. Again, I want to just remind that. Shared pair of electrons. Okay, dash. I have a model right here, little ball and stick model. Each yellow one is a hydrogen. We get a little bond in between, shared pair. There's your hydrogen molecule. Okay. Obviously, no matter what arrangement I look, even if it's going 3 dimensions, it's still going to be linear. Okay. If I look to another type of one, linear shape, and I kind of got it crossed off over here. Let me just get right off the screen. Okay. An example, BeCl2, beryllium chloride. Okay. Beryllium, if I look Lewis dots, there's going to be 2 electrons. Notice I separate them as I go around. Chlorine has 7. 1, 2, 3, 4. Now we double them up, 5, 6, 7. And of course, there are 2 chlorines. So here's your 2 chlorines. And now I think we all might be able to see that we have 2 available on the beryllium, and then 1 each on each chlorine. Okay? So obviously we're going to get a bonding and a bonding. This is actually an ionic bond, but it's still the Lewis dots allow us to show us this. All right, so there's our beryllium and chlorine getting together. Now notice beryllium, because it had the 2 unsharing electrons like that, the 2 available, I should say, like that, we might think it gets like this. But obviously you might be thinking, well, we're in the linear arrangement. It may not do that. And in fact, beryllium with chlorine is going to get in this a linear arrangement. And whoops, there's nothing on that beryllium. Okay, so I like to keep putting my unshared. All right, the reason that this happens is because of the VSEPR theory. All right, VSEPR, valence shell electron pair repulsion theory, and really the key is the repulsion here. All right, if you think about it, these are shared electrons. Okay, and if I grab my pen here, notice that it's in this 90-degree arrangement. Well, if electrons are negative, as they all are, then we have electrons here, and they want to repel. They want to get as far apart from each other as possible. So they're going to repel until they get as far apart as possible, which in this arrangement would be this linear arrangement. Obviously, can't go any further, then they start to get closer again. So linear arrangement is because the electrons want to repel and get as far apart from each other as possible. The bond angle, which you're going to see here, the bond angle is 180 degrees. So the 2 shared pairs of electrons on beryllium and chlorine is 180 degrees. Pretty simple, it's a linear. Obviously, any time you have only 2 getting together, like hydrogen and hydrogen, anytime you have only 2 atoms getting together to form a molecule, it's going to be linear. But in this case where you have 3, notice it does flatten right out and become linear.